Okay. Thank you very much. Okay, so my name is Ionut Schiopu. Like you can see, I'm from Huawei Technologies, Finland, more exactly the research center in Tampere. Of course, there is also a research center in Helsinki. And today we'll discuss about lossless coding of event camera frames. I don't know how many of you have ever heard about the event sensor or the event camera. Anybody heard about it? Okay, you have a few of them, you see. So basically, it's a new type of sensor that it has been developed in the latest years. It's a bit different than the RGB sensor that we all know. Basically, the difference is that every pixels works separately than the rest of the pixels. So basically, what you have that every pixel can generate an event at some specific position, X and Y, at some specific timestamp, and would generate a specific polarity. It can be positive or negative. So basically, what it signals is that the intensity that hit the sensor, that specific spot, it either increase with a specific threshold or decrease. So if the polarity is positive, that means the intensity has increased. If it's negative, the intensity has decreased. So now each event would be signaled using X, Y, polarity, and time. So in our case, we have to encode this type of data. It's event data, we call it, to compress the output of the sensor. Now, if you look in time, you have the figure 1 presentation of the events. You have at the bottom H and W, the height and the width of the sensor, and then the appearance of the events in time for each one of the pixels. Now you see that since the timestamp, the sensitivity of the timestamp is 10 to the power -6, that means this event camera actually it's said that it can actually generate 1 million event frames per second. So now if you conclude that's quite a lot of data that must be compressed, it's around gigabytes of data, a few gigabytes of data per second that must be compressed lossless and stored in the memory. So it's quite a lot of data. Moreover, since the computer vision algorithms don't consume this type of data as an event, usually what you do in literature is you accumulate these events during a time window of delta. So what you do if during this period an event occurs, you signal that event on the X and Y position of a frame. If no event occurred, then you signal that no event has been in that period of time. There are different accumulation periods. There can be a sum, there can be the first event that appeared or the last event that appeared. Different accumulation process can be applied. In our case, we usually use the sum, but it doesn't really matter for the compression algorithm itself. On the right side, you have the event frame, so what we are compressing. We have with the green, the non-event positions, and with blue and red, the positive events and the negative events. So positive polarity and negative polarity. So what you can see is there's quite a sparse information all around the frame that must be compressed. The idea is how can we compress this? Now in this paper, we actually propose a few ideas how to do it. Basically, we also had the requirement, the idea is actually to put this algorithm in a chip. So it has to be very simple, it need to have a low computational complexity, it has to be very fast, it can be, so that it can be hardened on the chip. You also have the requirement to provide random access to a specific group of pixels. So there are a few requirements, and you need to have compression, so it has to be efficient. Don't compress just 1 or 2 times, many times. Now, our contribution is that we combine 2 very well-known algorithms, round-length encoding and Elias gamma coding, into this algorithm that we propose. They were adapted for this type of data, and we actually propose 2 different algorithms. One is called simple and fast coding of large event frames. So we basically want to encode a huge volume of event frames at once. So this is designed for upper layer, let's say. But we also have a solution which is very fast and provides random access to any group of pixels, which is called memory efficient representation, or MER. So basically, the algorithm is actually quite simple, but we first need to understand what we need to compress. Since there are three types of signals that are contained in the event frames, we can codify them using three symbols, very simple signals, 0, 1, and 2. So 0 can signal a negative polarity, 1 a non-event position, and 2 a positive polarity. We can use also different non-efficient representation, can use them an A-B representation so we can visualize better maybe, although it might not make any difference. But anyway, in the end, there are only three symbols that can be codified whatever way you want. So the key idea is it's just very simple. We translate these trinary symbols, so trinary because there are three symbols, an alphabet of 3, into what we call key symbols. So instead of encoding 3 symbols at once, we actually encode only event and non-event positions. So it might be much more simple like that. So a key equals 0 will signal a non-event position. So it will encode the trinary symbol S equals 1, and a key equals 1 will signal event position. So trinary symbol 0 or trinary symbol 2. And of course, in that case, you also need to encode the polarity. Simple way is, of course, 1 bit to store a 0 for a negative polarity and a 1 for a positive polarity. And that's the basic idea that we propose. So on the right part, you have an example of 18 trinary symbols, which of course, a trinary symbol, since you have 3 symbols, must be stored using 2 bits. So that's 36 bits that you need to store. You need to allocate to store these trinary symbols. These are actually translated into key symbols. So the basic idea what we have to do is count how many consecutive symbols you have, key consecutive symbols you have. So on the right side, you have the key symbols. You can see that you have 6 key symbols where the key equals 0, then followed by 3, where, of course, you will need to encode also the polarities, and the corresponding polarities for those trinary symbols 0, 2, 0 will be 0, 1, 0, and then followed by another 9 non-event positions. So if you, in the end, the algorithm, what we'll do is encode a count 6, a count 3, write 3 polarities, then another count 9. So that's the simple algorithm that we propose. Basically, what we next need to do is to encode using an Elias gamma coding or Elias delta coding these counts 6, 3, and 9. We have here on the bottom an example how it is encoded using Elias gamma coding. You can see that the output is 18 bits, so you have a compression ratio of 2 in this case that I presented. Now, Elias gamma coding and Elias delta coding are quite simple. It's a traditional method proposed quite many years ago. The idea is that you first send how many bits you need to represent a number, and then followed by the number itself. So use the unary coding to codify the number of bits, followed by the number itself. So for example, if you look here at number 17, is written using 5 bits, 1, 3, 0, and a 1. What you need to do is you will need to send a 5, so number of bits. However, since the first bit is always 1, the leading bit is always 1, so you need to signal a 4. You signal that using unary coding, which is 4 bits of 0 followed by a 1. But if you notice that the remaining part from here is actually the number written in binary. So this is a simple code that can codify these not positive numbers, so from 1 till a huge number, if you want. The other version, the Elias delta coding, is quite similar. The only difference is that the number of bits is actually codifying using the Elias gamma code, followed by the number itself. It's a bit more complex, but it's more efficient, of course, in the case we have bigger numbers. You can see here, for example, for this huge number, 734, we have a reduction of the number of bits used for representation from 19 to 16 using such codification. Now, this is the algorithm itself. There are 18 lines, but there are quite many ideas that were introduced here. Basically, what we did is modify the run length encoding algorithm to codify two symbols, actually. So a key equals 0 and a key equals 1. Usually, you also need to send the key. However, in our case, we don't send the key since there is a binary representation. So it can be either 0 or a 1. So the idea is to first say what will be the first one, and the remaining ones can be usually deducted out of that. So what we do is we propose that the most frequent symbol that can appear will be a non-event position. So that's why we start with the supposition that the key is equal to 0. Of course, in such case, we might be wrong, because there is also a possibility that the first symbol can be an event position. That's why the very first count is actually, let's say, denoted K. It's actually encoded as K plus 1, so that you can cover the case if the first position is an event position. So what you do is go through the whole vector that you have. And for each one, you check in line 3, for example, if the key is equal to the symbol that you have. In such case, you increase K. Otherwise, if you found already the count, you codify the count using Elias gamma or Elias delta coding. And then if that key is a non-event position, that means you also need to codify the polarity, to write directly the polarity. So writing the polarity, since we propose this codification of 0, 1, and 2, it's actually writing the first bit in the binary representation of those symbols, 0, 1, and 2. And then you, of course, update the switch and the count. Now, at the very end, you also notice that we have to encode the last count. Now, the last count can be actually the whole sequence. So if the whole block is full of zeros or a non-event position, then you'll have a huge number that must be codified. So also, we signal that using the first bit in the binary representation, which can be set as 0 if there are several counts that must be codified, or as 1 if all of it is full of same symbols, let's say. I'll not go further because the time is running out. So the two ideas that we propose is simple and fast lossless event frame coding. Basic idea is we go through the volume and check if there is an event at that position, then we signal a 1. If it's not, then we signal a 0. And of course, when you find these 1 positions, we concatenate them, all of them, in a vector, which is codified with the previous algorithm. With this binary map that you have for the whole volume, you also codify them with the last algorithm, but you modify that to have only 2 symbols, 0 and 1. The other method is called MER. The idea is to divide it into blocks. Each block will have a specific size. You can divide it whatever size you want. But what we propose is to have random access to any block. So that's why you codify each block and you use a header to signal how many bits you need to represent each one of the blocks. So how many bits you need to encode or decode in this case, that specific block. Now, the experimental evaluation was done on the ETH training dataset of 82 sequences. We have a VGA resolution. We will show the compression ratio. We experimented 2 deltas, 1 millisecond and 1 microsecond. We compare with HEVC, VVC, the video coding standards, and some lossless compression algorithms, Calic and FLIF. Here are the results for MER. So for 1 millisecond accumulation period, it's clear to notice that the smaller the block it is, the less efficient the coding is. So the higher the block size is, the more efficient the coding will be. So here you see that the best results are achieved by 8x8 solution. Here are the results over the whole sequence for the state of the art. You can see that block-based compression is not efficient for this case. The single algorithm that provides a bit better solution is FLIF over 1 millisecond accumulation time. Please notice that our algorithms provide a runtime of around 3 milliseconds, the lowest one. depending on how many event frames are compressed at once. So you have a solution using one event frame, so save one delta using the delta, Elias gamma and Elias delta solutions, 100 event frames or 10K event frames. Please notice that for 1 millisecond, you have around 10 compression ratio. For 1 microsecond, it's around 1,000 compression ratio. These are my conclusions. Basically, you can have 2 milliseconds per event frame compression ratio, and the merge solution can be hardened into hardware. It's fast, it has a low complexity, provides random access to any group of pixels, and the solution for 1 milliseconds provides up to 13.7 times more efficient than the raw representation. So it will give you from thousands event frames to less than 100, let's say, event frames if you have a raw representation. Thank you for your time.